So we've just learned that the spherical harmonics are not eigenfunctions of the operator for angular momentum in the x direction or in the y direction. And we can come back to that, and exercise or example 6.10 in the textbook is a good example of this, and it demonstrates that there is no eigenvalue that can come out when we apply operators L sub x and L sub y to the spherical harmonics. So I'll leave you to go and look at that. But we may say, well, what's the key point here? And I'm going to again say that we recognize that y sub L, and that's this m in here. So our wave function is an eigenfunction to both the operator for L sub z and the operator for angular momentum squared, and that means that we can determine precise values of L squared and angular momentum in the z direction simultaneously. This also implies that the operators commute. Now what I'm going to show you is a relationship between quantum number m and quantum number L, and you'll recall this from thinking about the quantum numbers and the rules for quantum numbers for the atom that you've come across in general chemistry classes. So that's where we're going with this next part. We're going to think about the relationship between m and L, and I'm actually going to start by rewriting the two equations as shown below. So we operate now on y. I'm just going to start using superscript m in here. That's a superscript, and that's equal to now h bar m. So that h bar m is our eigenvalue. And we've also got similar equation here that we've looked at several times already. Let's write these down together though in one line. And again, let's just observe the fact that I'm replacing the j's from earlier in the chapter with l's. So that gives me an L times L plus 1 inside the brackets here, and then y L m theta comma phi. All right, so these are two eigenvalue equations, some operator equations. And what we can now do is we can actually square everything in here. So if I take this expression here and I square this, and when I do that, I'm actually going to combine these two equations. So when I square this, here's what I'm going to do. We will take L hat squared YLM theta comma phi, and I'm going to subtract. Effectively what I'm doing is I'm subtracting the equation on the right. No, I'm sorry, I'm taking the equation on the right and I'm subtracting the equation on the left from that. But I'm going to square it. So I'm going to square this whole expression. Okay, so I've got this part that's coming in here, and then the h bar m squared is what I get when I square this. Oops. And it comes in here, and of course I've got the h bar at the front. So what am I going to do with that? Well, what that allows me to do is to factorize the first part of the expression, right? And so the first part of the equation now becomes L hat squared minus LZ hat squared equals h bar squared, and I'll have these square brackets with the L now again, and then the wave function in here. Now, thinking of geometry, we can also recognize, of course, that the operator for angular momentum squared, that would be the magnitude of the angular momentum operator squared, that's going to be made up, thinking about the Pythagorean theorem and geometry, is made up of these three components. Okay, so we know this. So that of course means that this expression in the box in here is going to be equal to Lx squared plus Ly squared. So I can replace this, right? I can substitute this term in. So let's do that and rewrite. So we've got, so Lx squared hat plus Ly, it's Ly hat squared. Okay, now I've substituted that in. Go through h bar squared, that's L times L plus 1 minus m squared y L m theta comma phi. And so the observed values, so again remember the observed values here for this particular operator. So this is the operator for the sum of these two angular momentum squared terms. So I would write that the observed, it's easy to write it mathematically, the observed values of Lx squared plus Ly squared are, and it's going to be this L times L plus 1 minus m squared h bar squared. And of course we know this term in here, it can't be negative. We've got the sum of two squares. So therefore, what we can recognize is that this expression, this L plus 1 expression minus m squared, and that's, again, that's multiplied by h bar squared. And we know it can't be negative because it's the sum of two squares, so we're going to say that's equal to 0, or sorry, greater than or equal to 0. What we can now do is expand the brackets, right? So we're going to take this piece here and bring it over to the other side. So by expanding the brackets, we end up with L times L plus 1. Expanding the bracket, we've still got the h bar squared on the left hand side. That's greater than or equal to h bar squared and that m squared term. So we brought that over to the right hand side. Another thing we can think of now, because, so I guess since we know that L and m are integers, there's another thing we can write down. Well, we're going to cancel the h bars first, right? So we can cancel these h bars. But what we're going to recognize now is that L times L plus 1 is greater than m squared. And really, I guess since the L and m values are integers, we would now have to say that the magnitude of m is less than or equal to L. And if you think about this, if m was equal to 3 and L was equal to 2, so on the left hand side here we'd end up having 2 times 3, which is 6, and if m was 3, that would be 9. And so we'd say if L equals 2 and m equals 3, then we'd find that clearly 6 would be greater than or equal to 9, and that's not true. Okay, so that's incorrect. So basically what this means, when we think about it, this expression, I'm going to remove this term in here right now. What we'll say is that the rule that we have for quantum mechanics, this should seem familiar to you for the hydrogen atom. So the magnitude of m is less than or equal to L, and really what that means is that m is equal to 0, comma, plus or minus 1, comma, plus or minus 2, comma, dot, 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 all the way up to plus or minus L. And so this comes out from our consideration of angular momentum. What else can we say? So there's another conclusion I want to draw your attention to. So this other conclusion is that there are 2 L plus 1 values of m for each value of L.
I guess the size limitation prevents us from continuing on this particular video. So if you hop over onto the next one, things will continue. And there's about another 20 minutes to go before we finish this particular segment. Thanks for watching.